Okay. Remember when we had two vectors v1 and v2, and then we had some vector v, and we showed geometrically how a multiple of v1 plus a multiple of v2 could equal v. That would be a multiple of v1 and a multiple of v2 and a multiple of v1, anyhow. Okay, we can do this for any vector in this plane so that these two vectors here span R2. And they form a basis for R2 because they're linearly independent. One vector is not a linear combination of the other. It's not a multiple of the other because they have different directions. That's geometrically. Now, I'm going to assert that these two vectors form a basis of R2, and I'm going to call that basis B. Now, I want to express the vector 1, 3 as a linear combination of basis B vectors. In other words, a linear combination of these two vectors. Well, a linear combination of vectors v1 and v2 is c1 v1 plus c2 v2, and we're going to let that equal b, okay? Where b is the vector 1, 3, and v1 and v2 are the basis vectors. So that would be a linear combination of the basis vectors that add up to our vector b. Now, I could solve this symbolically, but I'm going to just do it with the numbers, and then we're going to generalize it to any number of dimensions and any number of basis vectors, well, the corresponding number of basis vectors. Okay, well, in this case, C1 times this vector plus C2 times this vector could be written this way, and that's equal to the vector 1, 3. Now, this reduces to, or this can be expanded and so forth, and give you a system of linear equations. It would be what? 4c1 minus 2c2 equals 1, and c1 plus 2c2 equals 3. That's equivalent to matrix equation. And if we understand that, and have done enough of that, we can go instantly from this equation, this vector equation, to this matrix equation. And we get the equation 4, negative 2, 1, 2, c1, c2 equals 1, 3. You can verify that that works out. If you expand this, you get the same system of equations you would get if you did this. And you get, what, 4c1 minus 2c2 equals 1, same thing we got up here. C1 plus 2c2 equals 3, same thing we got up here. Okay, now this is solvable if and only if the determinant is not 0. But we already know the determinant isn't 0 because these are the basis vectors. They're linearly independent, and a test for linear independence is whether this can equal the 0 vector, 0, 0, for anything but C1 and C2 equal to 0. If this matrix can be inverted, then C1 and C2 have to be 0, and that makes the connection with linear independence. Anyhow, we still want to check it. You know, for example, you know, I give tests based on randomly generated sets, okay? My random generator might screw up in a way that I didn't anticipate, and when I intended to give you a set of basis vectors, it might have given you a nonlinear independent set, okay? That wouldn't be hugely surprising, although I tend to be pretty careful about that. I do make errors. Okay, well, so you probably want to take the determinant, especially if it's 2 by 2. Clearly, you have an 8 here and a 2 here, and you can't combine an 8 and a 2 and get 0. So the determinant is not 0. So we can invert the matrix, and here's our solution. Here's our C1 and C2. Okay? So to express 1, 3 as a linear combination of these vectors, we've got to find the C1 and C2 that make C1 times this plus C2 times this equal to this. Here's how we find C1 and C2. And the inverse of this matrix, of course, it's a 2 by 2 matrix, so it's very easy to invert it, flip these two, change the signs of these two, divide by the determinant, and we get this. Now, you might not be able to read this, but you can do it yourself. In any case, this becomes 2/10, 2/10 here, negative 1/10, and 4/10. And if we multiply that by the vector 1, 3, we get, now, somebody impertinently pointed out that I'd done my arithmetic wrong here. I said 7/10, and it's 8/10. My eye picked up a 1 when it should have picked up when my brain should have fired on a 2. Because obviously 2 times 1 is 2, 2 times 3 is 8, and 2 plus 2 times 1 is 2, 2 times 3 is 6, and 2 plus 6 is 7, right? No, it's 8. Okay, so it's 8. You convinced me. So what we get for our C1, C2 is 8/10 and 11/10. Okay, well, I guess that's all we have on this board. So now we start, here we go, yeah. Okay, let's just see how the time's going. This video is getting too long. No, it isn't. Okay. I didn't know if I'd stopped the camera, but yeah, I stopped it and I started here. Kind of like, 2 plus 6 is 7. Okay, so we conclude then that the linear combination of these two vectors that add up to this one is C1 times V1, 0.8 times the 4, 1 vector, plus C2 times V2, okay, 11/10 or 1.1 times the -2 basis vector. And then we can verify that. 0.8 times 4 is 3.2, 1.1 times -0.2 is -2.2. Add them up, you get 1. And 0.8 times 1 is 0.8, 1.1 times 2 is 2.2, and 0.8 and 2.2 gives you 3. So we verify that we actually got a correct solution. Now, we use a little notation, or introduce a little notation. I'm going to say then that the vector 1, 3 is equal to the vector 0.8, 1.1 relative to the basis B. Meaning, of course, 0.8, 1.1 relative to basis B means 0.8 times your first vector plus 1.1 times your second vector. Now you might wonder why we go to all this trouble, but you'll find out. Okay, this is extraordinarily important. And extraordinarily powerful. Okay, so yeah, we say this because this vector is 0.8 times V1 plus 1.1 times V2. It's pretty much what I just said. Now we want to generalize this process, and it's actually pretty easy to generalize. By generalize, we mean we want to be able to do this for any space of any dimension and for any basis. Okay, so, well, in general, your space has a dimension that we can call n. That's what we usually call the dimension of a space, unless we've already used it and then we have some other name. And the basis is going to be just represented. We're not going to use numbers or anything. That would be specific. We're trying to generalize this. Generally, your basis is going to consist of n vectors, linearly independent, spanning the space. And that's implicit in saying that this is your basis, okay? Because B does stand for basis, as we did here. So we want our vector B, remember here, we wanted a sum of basis vectors that equals 1, 3, right? Well, 1, 3 took the role of the B vector here, right? And V1 and V2 were the two basis vectors, and C1 and C2 were the coefficients of those basis vectors. So B is going to equal something with respect to B. And of course, the fact I have a B here, the fact I have a B here, this B is basis. The use of B in the equation AX equals B is just something we did a long time ago. So it's just coincidence that we have the same letter, but this is capital and this is small, so they have completely different meanings. B is the vector that we're going to get, or is any vector in the space, and we want to be able to express it in terms of the basis big B. Okay? So, B is going to be any vector in the space. Well, let's call that then the vector x1, x2, up through xn. These are semicolons, so this is really a column vector. Then we're going to call the vector B with respect to basis B. Well, that's what our C1, C2 was over here. So we're going to call it C1, C2, up through Cn. There might be better notations, but that's what we're going to use. Okay, so That's what we're trying to find. We're trying to find the C1 through the Cn, and that's what we're going to put in here, and that's going to be our B vector expressed relative to basis B. Okay? Now, the thing that relates this to this is our matrix of basis vectors. Okay? Now, let's remind ourselves what this is. Over here, the 4, 1 vector we expressed as a column vector, 4, 1. The negative 2, 2 vector ended up expressed as a column vector here. We didn't do that arbitrarily. There's not a rule that says we do this with the column vectors. It follows from the fact that we have C1 V1 plus C2 V2 equals B. We write that out, and we get this matrix equation, and that's where the basis vectors end up. So it's not a magical formula or anything. It's where the basis vectors have to end up if we write out this equation that says linear combination of the basis vectors is equal to our B vector. Okay? Well, you get the same thing here. Just you got more basis vectors, so you just put them in the columns. Okay? And then you say, well, that times the basis vector, or times the B vector relative to our basis is equal to the B vector. Okay? And that's exactly what we had here, because our C1, C2 was this vector relative to this basis. The solution is simple. Our solution, our vector with respect to the basis B is just the inverse of our matrix of basis vectors in the columns, the inverse of that matrix multiplied by the vector that we started with. That's the vector x1 through xn. Okay? Now, instead of calling this vector B and this one B sub B, I didn't want to introduce the notation here. I wanted to keep the notation close to the notation that we had here and the notation we're used to. But I'm going to start calling this vector x. It would make sense since I said B was x1 through xn. It wasn't b1 through bn, although I could have done that. I made it x1 through xn. So let's call this x, and let's call this x sub b. So now, we're going to use x instead of b. So writing the same thing here, we have x sub b equals the inverse of a matrix, and we'll call this matrix P, times x. Okay, so we've just replaced. So now, instead of calling this b sub b, I'm going to call this x sub b, and I'm going to call this x. And I'm going to call this P. Okay, P is our matrix made up of the basis vectors in the columns, again because of the way the equations come out. So it's going to be then x sub b equals P inverse times x. Nothing particularly surprising about that. So this just says, okay, we've worked it through, we understand it, hopefully, and this summarizes everything we understand. That our matrix x, or our vector x, relative to the matrix B, is expressed as x sub b, and x sub b is equal to P inverse times x, where P is our matrix of basis vectors. Okay? So this is just shorthand notation for all of this and for everything we understand in terms of this and understanding why this works. Okay? And again, I specify P as our column, our vector where the basis, our matrix where the basis vectors are in the columns. Well, that's great. Now what happens if we have a different basis? And we, for some reason, and there are plenty of good reasons, want to relate x with respect to basis B to x with respect to basis B prime, where B prime is just another set of n vectors, linearly independent vectors spanning the space. Well, that's what we're going to look at next.